So for today's video, we are going to practice writing our own products from a synthesis reaction equation. I have my practice page handout, which is also basically our notes today. The best way to practice writing equations is not to me to talk at you, is for us to actually practice them together. But I also have my red and blue colored pencil. I also have my periodic table. If you are still needing the security blanket of this red and blue with the charges on top, maybe try to start using a blank one. I am going to pull the red and blue one out to where if you are struggling or a new student trying to write formulas for the first time, you will kind of hopefully have this as kind of a little bit more of a home base for us. Okay, but for a synthesis reaction, typically if I'm going to have you write a synthesis reaction, it will be making an ionic compound, meaning I will take a metal single guy and a non-metal single guy and girl, whatever, and then they will make a couple, an ionic compound, okay? So when I have my little scaffold thing, or my little, what am I trying to say? My little representative of what a synthesis reaction entails, I will most often show it as A, I'm taking a metal, and B, taking a non-metal to make an ionic compound A, B. Okay? So, it says a synthesis reaction is a reaction where two or more reactants combine to make one product. So the most common one is you're going to be making an ionic compound for me, where I take a metal, and I'm going to underline that, will combine with a non-metal to make a salt. I mentioned, I think in one of our previous videos, that a salt is just a general term for any ionic compound. Okay, so for our first example right here, we have lithium. Lithium is totally a metal on my periodic table. So I got a red metal here. Yes? And then nitrogen, he be right here. He is a blue non-metal on the periodic table. So if I give you these two things and I say figure it out, well, you're going to look and be like, okay, I got one element and one element there. They are two single people. I will be making a couple because that element is a metal and that element is a non-metal. I will be doing a crisscross to figure out the ratio of ions in an ionic compound. So this is my ionic compound. I have lithium nitride. Okay, y'all are like, but what about the numbers? The numbers is the most difficult part of all of these reaction predictions, or writing our own reactions. We will take it step by step, I promise you. But like I mentioned, these ionic compounds are going to be the main ones that we will be writing reactions for. So I do want to make a couple of notes over here. I want to make sure that you will be dropping off all subscripts from the reactant side when it comes to the time, or comes to the point of you trying to create a new compound between those two single people. You're like, well, what is she even saying? It will make sense when we get to our first couple of practice examples. So we're going to write drop all subscripts from previous reactants. And then we're also going to write crisscross. Okay, so I'll actually be making new subscripts that may look different than the numbers that I had here underneath, maybe like my nitrogen here. 2 has disappeared. That is because I have dropped that nitrogen subscript. Okay, he is not necessary. I'm now nitrogen in a couple, right? So I'll have to figure out the subscripts according to what that ionic formula needs to be. Okay, so that's the first option, the most common option by far, especially for first year chemistry, is I will simply have you create an ionic compound for me in the terms of now being a synthesis reaction. I can also have two nonmetals. Okay, if my two nonmetals, my single people, so if I have two nonmetals, right? So in this one I have a carbon and I have an oxygen, right? Well, if I see that coming, I'm like, okay, I've got to make a covalent compound because two nonmetals make a covalent compound. Now, this one is not something I will give more. This is something I will not usually give you because you can't do a simple ratio of ions with the crisscross to figure out what the subscripts are from that synthesis of the two elements, right? I would have to give you a little bit more information. Usually I will actually, like the very last problem down here, I have to, in words, tell you what I want you to make the product look like, so you'll know how many sulfurs and oxygens that will be represented in that compound, okay? So there's maybe one or two examples of these covalent compound forming synthesis reactions that we'll get to. But yeah, let's just bounce on over to doing some practice for us. We like some good practice. Okay, so I do have out my red and blue colored pencil because that is a great thing to get us started. I do have out my periodic table. It says complete and balance the following equations. Actually, up here at the very tippity top, I want us to remind ourselves of our diatomics. We know my diatomics. They are Hofbrinkel. We got hydrogen, and then we got these guys that make a 7: nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Okay, so those 7 guys, if I'm writing them as single people, they come in twos. So I'm going to write diatomics are hydrogen, oxygen, fluorine, I don't know why I'm doing but why not? So Hof and then Brinkel, so bromine, iodine, nitrogen, and then chlorine. Now let me be clear, they only get 2 if they are just by themselves. I'm like, make him a single person. If they come into a couple with somebody else, no, they do not come with a 2, okay? You will figure out if they need a subscript based on who it is they are bonding with, the result of that crisscross. Okay, so now we are ready to get going. I'm super excited. What I think might be helpful actually is just to, with my reds and my blues, identify if the examples that I'm giving you are going to be forming an ionic compound or a covalent compound, depending on what types of elements you see here on the reactant side. So for example, I got lithium right here. Woo! Lithium is a metal. I got iodine right here. Iodine is a non-metal. So I know I'm going to be making an ionic compound, so I can totally even write an I off to the side to get my brain the way it needs to be. I got magnesium, a metal, nitrogen, a non-metal, another ionic formation. I got sulfur. You're like, oh, I know what she's doing now. It is a non-metal, but what is strontium? Oh, it's a metal. She just wrote it backwards. That's okay. That's okay. I can give you the reactants in any order, but you better, when you make my ionic compound, make sure that that metal is written first, and we will get there. Here's something fun. I've just given you some words. So for these problems, the last half of this page, I'm going to actually have you write formulas not only for the product that you're trying to make, but also like for your reactants. We're going to try some of that too, okay? Regardless, I can identify these as ionic or covalent. I got magnesium, a metal, oxygen, a non-metal, ionic. Next one, I got silver, a metal, oxygen, a non-metal, ionic. Oh, here's super fun, super fun, super fun. I got hydrogen and chlorine. If I am bonding hydrogen, who is a non-metal, but with chlorine, this is me doing an acid, which an acid also is technically ionic. So I'm going to put a little I in parentheses, because the process of writing a formula for an acid is the same crisscross mentality of understanding the charges of both of those ions and what ratio I need of both to where it is neutral. Okay, next up I have iodine. Okay, that's a non-metal. And oh, sodium, there's my metal. See, I got so many ionic compounds. You're like, they all ionic except for this last one. I only gave you one covalent because, like I said, it's hard to predict the products of a covalent because you don't know how many of each one of the elements you have when you get them together. Okay, so I told you I want y'all to make sulfur trioxide, so that's a covalent compound. Okay, so now we're in the right frame. So lots of ionics, which is why I had you guys up here at the top. Figure this out. Crisscross, crisscross, crisscross. Okay, so we are ready to go. This is amazing. I'm super excited. If you need to, like, have a little bit of space off here to the side to write and set up your crisscrosses to remind you how we write ionic formulas, that is super fine. You take all the space you need. Okay, now I want to look here. I've got lithium. Plain old lithium. He is not one of my diatomics, so that's why he does not have any subscripts or numbers around him. Li, there he is. But I gets a 2. even when he's single, or when he is single, because he is one of my diatomics, okay? And if I kind of just glance down here, the only single people who will get any sort of a subscript are going to be my diatomics, like my nitrogen, also here in the next example. Okay, that's great. So you're like, let's make a couple. Drop any subscripts that you have on the reactant side. When you form a new relationship, you are not going to bring any of your baggage from your previous weird single life into a relationship with the person you were trying to look good for, right? So that means that when I'm setting up my crisscross between lithium and iodine, I do not want to see any numbers down here on the bottom. Okay, then I look at the location of each one of these elements on the periodic table to grab what charge ion they make. We know that lithium makes a +1 charge. And iodine, he's in group 17. He's a halogen, so he makes a -1 charge. So what that means is I need a 1-to-1 ratio of those elements to each other. So I'm going to write Li, I. So the result of that crisscross ones, I have a 1-to-1 ratio. Now, the last thing I'm going to do, you are all freaking out. You're like, but there's a 2 and it would disappear. Yes, we balance at the very, 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 very end. So I will pop out here a little blank for us to be able to accommodate for it. So the thing that kind of trips y'all up at first is y'all get so hung up on wanting to drag stuff over from the reactant side to the product. No. Previous baggage from what you were before you went into a relationship. Get it out of here. Okay, so we're going to balance at the end. So it looks like in order to balance, I got 2 iodines on the reactant side. That means I need 2 over here. So let's start by putting a 2, right? And then that means I have 2 lithiums, so I can get 2 lithiums on the reactant side by putting a 2 there. That is a balanced reaction equation. We just did it. We made a synthesis reaction. Look at this. And y'all, we have formed an ionic compound. One thing I want you guys to notice is that in any ionic compound, the red metal is written first, okay? Amazing. Okay, next one. We got magnesium and nitrogen. The only reason nitrogen has a 2 is because he's one of my Hofbrinkels, right? He always comes in 2s when he's single. When I'm setting up the crisscross, drop the subscript from nitrogen. Everybody comes in fresh, looking nice for their new partner with no baggage from the previous life, right? And I got to figure out what their charges are on the periodic table. Magnesium, he's totally got a +2 charge because he's in group 2. Nitrogen, he's in group 15. He's totally got a -3 charge, yes? So to neutralize these 2 ions, I'm going to need 3 magnesiums for every 2 nitrogens. That's what I mean when I say crisscross. I'm not caring about the positives and negatives. That's just a way for me to figure out how many I need of each ion based on the magnitude of their charge. So my formula for magnesium nitride is going to be Mg3N2, okay? We always know we balance at the end, okay? But one thing I do want you to know, how cute and convenient that N also has a 2 on the product side like he does on the reactant side. Yeah, that is just by coincidence because he was forming a compound with a metal who had a +2 charge. That is not dragged over from the reactant side, okay? I had to create that new subscript from the formation of this compound. Okay, but I do have a metal and a non-metal. We love that. Okay, so I'm going to balance. Y'all ready to balance with me? It looks like, oh my goodness, I got 3 magnesiums on the product side, so how about I give myself 3 on the reactant side? And then I think we're good. Look, the nitrogens are already balanced, so we love that. We have written a synthesis equation for the formation of magnesium nitride. I love that. Okay, this one is one of my favorite ones. If you'll notice my 2 single people, nobody's got any subscripts because neither sulfur or strontium is in my Hofbrinkel diatomic list. So I'm going to make an ionic compound because one is a metal, one is a non-metal. But be careful. The person who goes first is always the metal. So I've got to set up strontium first, okay? Strontium is in group 2. Group 2, they lose their 2 valence electrons to where they form a +2 charge. And sulfur is in group 16, where they gain 2 electrons to satisfy their octet. So they will form a -2 charge. This is wonderful. This 2 and 2 charges means I have a 2-to-2 ratio or a 1-to-1 ratio of both of these ions to each other. So I have SRS, right? Balancing at the end. I don't need to balance. It is already balanced, which is already always super exciting for you. So the main thing I want you guys to look at what we've done here is for each one of my synthesis of ionic compounds, I have the red metal written first and the blue non-metal cation written second. Okay, now let's push it a little bit further. Instead of me already giving you the formulas for the reactants, I'm like, you give them to me. You guys are smart, right? You're like, oh, I don't know what to do. Yes, you do. If it is anything but a Hofbrinkel, just write the symbol of that element. Magnesium, great. What does he look like? I love that for him. Yeah? Oxygen. Oxygen is a diatomic, and because he is a diatomic, he actually looks like O2 when he is single. Now we're set up exactly like what we just did on the opposite or on the previous examples. We are ready to go. That's an ionic compound between a metal and a nonmetal. Set up a crisscross. Get rid of the original subscripts that they had on the reactant side. I need to know how many magnesiums to oxygens are required according to their charges. Magnesium's group 2 plus 2 charge. Oxygen always has a -2 charge. So this is a 1-to-1 ratio of magnesium to oxygen. So I got MgO. Last step for all of my writing chemical reactions is to balance at the end. I always like to put a space there because that is my reminder that I will not walk away. Putting a space is not required, especially since sometimes it looks silly if you don't put a number in there, but that's okay. Also, if I'm going way too fast on like, how is she getting this formula and what does she mean when ratios and whatever, please go back to Unit 5 and watch all of the videos I have supplied for you on ionic nomenclature, okay? Because that's what we're kind of actually using today, just now expanding it to where we're putting them in chemical reactions and then balancing and stuff. Okay, so it looks like I got 2 oxygens on the reactant side, which means I need to put a 2 in front of MgO or magnesium oxide, which then means I will need a 2 for the magnesium on the reactant side. Amazing. Okay, next up we got silver and we got oxygen. Oxygen's diatomic, but silver sure is not. So silver is Ag, and oxygen diatomic O2. Now we couple them up, drop any subscripts. What is going to be the ratio of any silver to any oxygen? Remember my silver, he's that transition metal who always has a +1 charge, so this is part of my +1, +2, +3 arrow. So if you ever see silver, zinc, or aluminum, you will know their charge. Any other of my transition metals, I would have to provide more information to you so you know what you would be using to set up for that ionic crisscross. So it looks like my formula is going to be Ag2O. So silver oxide looks like that. So here I formed silver oxide, right? And I'm looking, I'm like, okay, I need to balance. What are we going to do to balance? Well, looking here, I got 2 oxygens on the reactant side. So I'm going to put a 2 in front of silver oxide to give me that 2, because remember the coefficients get distributed, which then gives me 2 times 2, 4 silvers. So I'm going to put a 4 here. Also, if I'm going too fast on balancing right now, I have the previous video to this was an entire practice page on me walking through balancing very, very, very slowly. So I hope that you go utilize those videos and not expect to get all of the extensive amount of information just in this, especially since we're learning this new concept of writing our own chemical reactions, right? Okay, now we know we're going to make an acid here between hydrogen and chlorine. Okay, hydrogen, single, hydrogen. He's one of my diatomics, so he is an H2. We love that. And then chlorine, also one of my diatomics, right? So Cl2. That's great that they have subscripts as reactants, but that's when they're single. Drop those subscripts, set up the crisscross. Hydrogen in an acid, he's trying to act like one of his buddies here in group 1 who's an alkali metal who makes a +1 charge, right? And chlorine, he is in group 17. The halogens always make a -1 charge. So the ratio of ions that I need in hydrochloric acid are going to be a 1-to-1 ratio. Balancing at the end, we have, looks like 2 of both of these guys on the reactant side. So how about we get 2 of both of them on the product side by putting a 2 in front of the hydrochloric acid? Amazing. Look at that. Look at this, you guys. I'm very excited. Okay, next example, iodine. Iodine is a Hofbrinkel. That means single iodine comes in twos. Sodium, not a Hofbrinkel. He is plain old Na from my periodic table. Just like one of the previous examples where I wrote the nonmetal first, that is great and totally appropriate when they are by themselves as reactants, but when you were showing them making a couple for me, you better make sure the metal cation is listed first in the formula. And so the formula, figuring out what charges they have to each other. Sodium is a +1, iodine is a -1, which means my formula for sodium iodide is Na. A 1-to-1 ratio. I didn't even draw my arrow. Oh my goodness, what is going on? Okay. Now for balancing, let's see. The only discrepancy I have is I've got 2 iodines over here, so I need 2 over here by putting a 2. Well, then that made me have 2 sodiums on the product side, so I got to put a 2 here as well. And we balanced. Hooray! Okay. Last one. This is our only example of a covalent compound. There would be no way for you to know how many sulfurs and oxygens I want in the covalent compound that I'm wanting you to create without telling you, okay? But you can have synthesis reactions where you make covalent compounds, so I thought I would provide one for you today. Also, a lot of the nonmetals that are involved in covalent compounds tend to be diatomics. We got a lot of heavy diatomic representation in my nonmetals, so it gives us another opportunity to practice writing our diatomics down. Sulfur is not a diatomic, though. He's just plain old S. But oxygen totally is, right? And I'm telling you I want to make sulfur trioxide. According to our covalent nomenclature rules, that tri means I have 3 oxygens. I do not have a prefix in front of sulfur, so that means I only have 1 sulfur. So in sulfur trioxide, I would have SO3. Okay, but I will now make you balance at the end. Do not walk away from the balancing situation here. And it looks like I got an even, odd, double the odd on the oxygen here. So I'm going to start off by putting a 2 in front of sulfur trioxide. That would give me 6 total oxygens, which is then is a quick fix over here by putting a 3 in front of my O2. That's also 6. And then to give me the 2 sulfurs that I've created here, I can put a 2 in front of that sulfur on the reactant side. So what we've just done here, the theme here on my synthesis is, now diatomics are actually super important for us to really know. And then for my ionics, guys, get rid of the subscripts from the previous reactant past life side, okay? When you form a new couple with somebody, you want to come with your best self forward and none of that baggage present. But we have now been able to write our own synthesis reactions, which is super exciting.